Hi, today I'm here to talk to you about delivering application assurance with SD WAN. Have you ever thought about how network technologies impact you as a consumer when you're out shopping? Maybe you're swiping a credit card at a checkout at your local retailer and you want that transaction to be quick and painless, frictionless. Or when you're at a cafe, maybe enjoying some coffee and some free Wi-Fi. That experience really has a big impact by the technologies working under the hood. Today we're going to talk about how those technologies impact us as consumers and users. Today I'm going to talk to you about three components of application assurance. First, and probably most important, is the user experience impact. Second is broadband challenges. These are the things that are associated with using the internet to connect our distributed networks today. And third, talk about a variety of QoS technologies that are available from a variety of suppliers in the industry today. Let's set the stage and take a look at what IT is set out to have their objective. They are looking to deliver a consistent user experience. Why? When you think about it, IT organizations service large networks with hundreds and thousands of endpoints in these distributed networks. Each one of these branches or stores has users that consume this technology. And whenever there's a problem or an application fails, for example, that creates a phone call or a ticket back to the central office where IT staff has to shift their time away from working on strategic initiatives to grow the business. This is why IT organizations are looking to source and qualify technology solutions that deliver a consistent user experience in today's heterogeneous network topologies that we have. This also creates a unique problem set. We all have more applications that sit on the WAN or the LAN inside our branch that actually fit across the WAN. And when this happens, when applications contend for bandwidth out over that WAN, this is what creates congestion. And this is what kills the user experience. This is what slows down transactions and impedes application performance. Luckily, there is a solution. There's two main things that SD-WAN solutions today employ to solve this problem. They either slow down individual applications, and ideally you want to make sure you slow down your lower priority applications to make sure your higher priority applications get through, or you actually move applications to another path. In today's SD-WAN environments, we commonly have two or more connections. So that's a very viable solution to take advantage of multiple connections. Let me talk a little bit about the application assurance framework to put things in context for my discussion today. So on the input of this matrix, you have all of your applications. These are the applications that are coming across your LAN and contending for that WAN bandwidth. And we know we need to do a set of functions to make sure that they fit through properly. First, you have to be able to identify these applications. And this is in a business context. So when you create network rules and policies, you need to be able, an administrator needs to be able to write rules that are put in context of the business from their application perspective. So this means writing rules that describe email, Office 365, Salesforce, Workday. This is not writing rules about IP addresses and ports. That's a thing of the past. Second, you have to be able to have technology that classifies applications into the different priority levels. There's a lot of priority levels depending on the solution you have, and it's important to know, and we'll talk about that today, that depending on the type of application, it behaves differently and needs different attention to the type of classification. And third, you have to have a prioritization schema. This is technology and algorithms that have the ability to assign the right amount of bandwidth to the right applications so that on the output of this framework, you actually can deliver a consistent and good user experience. So let's talk a little bit about the broadband challenges that the internet presents us with today in the SD-WAN context. So the data that we're looking at here in this chart is actually generated by the HughesON Technologies. And this technology has the ability to measure with very fine granularity the amount of available bandwidth that is delivered right to the last mile at each branch location on each circuit. And so it tracks this over time, in real time, actually up to 4 times a second. And so with this granularity, we can see that on this graph, over a 24-hour period, how the available bandwidth varies pretty widely in this particular sample that shows an average over 5 sites from a table services restaurant. And you can see that upwards of a 7 megabit per second swing in a 1-hour time frame presents a challenge. When we're deploying and developing these QoS technologies, we need to have the ability to react and adapt to such big changes in bandwidth. This particular graph here emphasizes that the problem I just described in the last slide really exists at scale. So for a 1,000-site network that has roughly broken up evenly by 1/3 cable, 1/3 DSL, and 1/3 other, you can see that over a 24-hour period, the bandwidth varies by hundreds of megabits. And in a 6-hour time frame, that can actually range by upwards of 500 megabits per second. So while you can have that variation of 7 megabits at an individual site, you can tell that this 500 megabits accounts for variability across many different sites. This again emphasizes the need for technologies to adapt to these rapidly changing conditions. Next, we have this particular graph that shows not only do we have to deal with the bandwidth variations with broadband circuits, but also with their quality. Their quality changes over time with these conditions we call brownouts. These are examples of conditions that are created when there's congestion in a provider network due to oversubscription and the usage of the whole system going up and down based on people coming home from work and going back home. These conditions in these broadband networks create a large amount of variance that actually turns out to be an impairment in the network. So this particular graph shows that on average, 17% of a 1,600 site financial services network is actually impacted by these brownouts on a daily basis. And you can see that it varies over time on a daily basis. So this is relatively unpredictable. Again, just drawing the conclusion here that we need technologies that can track and adapt to these big changes over time. Now I'm going to talk about 3 types of quality of service that are employed by most SD-WAN solutions in the market today. First and most important is the ability to do bandwidth management or traffic shaping on individual links. So these are technologies that allow individual links in a multi-link broadband environment to optimize the links independently, so that in the event where you might only have one link available, this technology is critical to controlling that user experience. Second, we have path control, sometimes called intelligent path control or multi-path optimization. These are technologies that use multiple links together to distribute applications across it. And this is important, again, when individual links fail. We need to be able to move applications around quickly and seamlessly. Third, we want to be able to use an FEC or a forward error correction technology, also known as replication or duplication technology, so that for the highest availability architecture configuration, we can take a single application and send it across multiple links. So let's dig a little deeper into what traffic shaping really is. So if we look to a trusted source on the internet, say TechTarget, they're a good example of general knowledge that helps us kind of understand what these technology terms mean. They quantify traffic shaping as regulating data transfer to enforce QoS or to assure QoS. And they go on to clarify that by saying, in order to do that, you need to be able to delay the least important traffic. And that's a key capability of traffic shaping. Keep that in mind as I go through some more examples here. All right, let's take a look at what traffic shaping looks like in a real-world environment when running on a broadband connection and when we encounter congestion. So in this particular example, we have 2 10 megabit per second broadband links, probably operating at different stores because they have different technologies. And what you'll see is that by that white wavy line on the top, that represents the available bandwidth changing over time. As we talked about earlier, that's a challenge with broadband links. In the legacy state of MPLS and T1s, this was a fixed capacity, was very easy to track. So if you look, the top link represents when we're running traffic shaping, and the bottom link is when we don't have that on. So as the applications come in and fill the link, you'll see we have 3 different applications we're demonstrating here. Your business critical, real-time voice over IP traffic, for example, on the bottom, that's your first priority, your highest priority. Second, in the dark blue, we have transactional. This is an example of credit card or point of sale transactions, also business critical. And then on the top, we have our lower priority batch traffic, such as Dropbox or email. And so this lower priority traffic is an example of of traffic or applications that elastically grow to fill the pipe. And these create the conditions of congestion. So when congestion actually happens, what you'll see is that on the link that doesn't have traffic shaping, you have this chaos that happens on the wire. All these individual applications are contending for the bandwidth, but none of them are it's not being able to be handled in an orderly fashion. So what happens? Packet loss happens, latency goes up, transaction times go down, and individual applications are forced to govern themselves. And they do that because TCP-based applications end up retransmitting data. And this congests the link even more and creates a poor user experience. And this is what becomes problematic when you don't have the ability to adjust to that available bandwidth. So on the top link, what's critical to note here is that this traffic shaping technology tracks the available bandwidth. And that's important because we need to be able to squeeze the applications into what's available. And so what happens is that we are able to, in this particular mode, guarantee a consistent user experience for those business critical applications because we know how much bandwidth we have. This allows us to guarantee available bandwidth to those critical applications while squeezing those lower priority applications to fit in what bandwidth we have left over. All right, let's take a look at what path control looks like when we couple it with traffic shaping. So in this particular example, we have a dual broadband WAN, for example, deployed at a branch network. And commonly in a broadband network, we look to deploy diverse technologies. And commonly what that means is that your primary link is of a higher quality and your backup link is usually a little bit lower quality, maybe a little bit cheaper. And what that means is that typically your primary link has more bandwidth and lower latency, and your backup link has less bandwidth and higher latency. So as I was describing in the previous example, we have that same three set of applications running on WAN 1. And because we have path control, we can actually distribute applications across multiple paths, so we put some other traffic on WAN 2. Now let's take a look at what happens when congestion happens. So in this particular scenario, similar to the last one, where the bulk traffic, such as Dropbox here, grows and elastically fills up the link, what happens is that causes the policies that we wrote for that primary WAN on WAN 1, where we set the policies to be able to adjust applications to other paths when performance thresholds go out, when performance doesn't meet a certain threshold. So when packet loss or latency is introduced on that primary link, those applications move to that backup link. So what happens is congestion on the primary link actually causes those applications to switch the backup link. And so this creates a couple of different problems. When we move all those applications back to over to that backup link, they're all contending for bandwidth because they no longer fit in that smaller pipe. This creates congestion and really degrades that user experience. If that backup link has a data plan, for example, such as LTE, this is an example of where our applications spend more time on that backup link. That ultimately drives up our costs, and that will make the CFO pretty mad. Now, you'll also notice that on the primary path, what happens is those batch or lower priority applications actually dominate that high-quality primary link. And this is kind of against the objectives of what the business is trying to achieve. So finally, let's take a look at what path control looks like when you combine it with traffic shaping. So just as we showed earlier, we have the same set of applications. So when they come in and when congestion starts, what you'll see is that on the primary WAN, all the applications are able to stay on that path. And so we're able to guarantee that consistent user experience for those business critical applications. That allows us to guarantee that bandwidth and also allows us to be able to let those lower priority applications fit. And that also allows us to give typically more available bandwidth and a better user experience even to those lower priority applications because there's commonly less bandwidth available on that backup link. And that leads to a better user experience. All right, let's take a look at what a real-world application assurance success story looks like. The data that we're looking at here is from a Hughes deployment. This particular customer deployed voice over IP over the broadband network that Hughes delivered. And what you'll see is that on the scale, we have the lower scores are poor and the higher scores are good or better. And this is what is represented as a MOS score, a mean opinion score, which is a metric to measure voice quality. And so you'll see that that's represented by the happy faces on the right-hand side of the slide. The angry face on the bottom is not good. So you'll see that when there is no QoS on the link, the quality of the calls varies widely, from poor to good. Once we turn on traffic shaping, that actually really allows the user experience to greatly increase. But not until we combine all three technologies, traffic shaping, path control, and FEC, are we able to deliver the best user experience. And that's the key thing to remember here. So a couple of key takeaways that I want you to remember coming out of this talk is that congestion is what kills the user experience. Having too many apps on our LAN that don't fit across our WAN creates this scenario that we just have to choose the right technology to deal with. And when you want to deliver the right application assurance framework, you need to make sure that you have a combination of all three of those technologies. Dynamic bandwidth, dynamic traffic shaping that allows you to adapt to the changing conditions of the broadband networks that are comprised of the internet today. Path control that allows you to move them around. And finally, FEC technology that allows you to deliver the highest availability. And with that, I want to thank you for your time. I want to encourage you to reach out to me on social media, and let's continue the conversation from here. Thank you.